So yesterday we discussed about the continuous charge distribution. You can check that video. Okay. And now we are going to see some applications of continuous charge distribution. So we are going to find out the electric field due to continuous charge distribution. So let's consider first example, the electric field due to a semicircular ring. So we'll consider a semicircular ring and we'll find out electric field due to that semicircular ring at the center of the ring. Okay, so let's suppose this is a ring and there is some charge. There is a charge q uniformly distributed on the length of this ring, okay, over the length of this ring, and we want to find out its electric field at the center. We want to find out its electric field here at the center. So now how should we proceed? So what we do is we define linear charge density. So because this is a long body, we'll define linear charge density. So linear, I'm sorry, charge density for this ring. Lambda is equal to charge divided by length of the ring. So how much is length of this ring? If R is the radius, if capital R is the radius, then length would be equal to pi r. If it is full circle, the length would be 2 pi r. Okay, this is semicircle. That's why the length is pi r. So it is q divided by pi multiplied by r. Okay, so this is the linear charge density. Now, what we do is, see, we'll consider some small length element on this ring. So let us consider a small length element here. Okay, so the length of this element is suppose dl. How much would be the charge on this length element? So charge on length element dl is suppose dq. Okay, and the charge is uniformly distributed. That's why we can say charge is equal to what? Q is equal to this linear charge density multiplied by the length, right? So dq would be equal to linear charge density multiplied by length of this element. Length of this element is dl. So it is lambda multiplied by dl. That is the charge on this length element, right? Then we can find out the electric field due to this charge at this point. So for this charge, the electric field would be radially outwards, right? The electric field due to this charge would be radially outwards like this. Okay. So electric field would be radially outwards. This is the electric field. So let's call it dE bar. So dE bar is the electric field due to the small length element. Now we can resolve it along two components, but before that, see, this is this length element. Okay, if we join this line, if we join a line from the midpoint of this length element to the center of the ring, it makes some angle theta with this vertical line. Let's call it y-axis. So it makes some angle theta with the y-axis. So now we have this length element on one side of this ring. We can have similar length element on the other side of the ring. Okay. So we can have a length element at the same length, at the same angle on the other side of the ring, right? And of the same length. So it will also create the same amount of electric field at this point, right? This length element has the same amount of charge because its length is equal. So it will also produce same amount of electric field at this point, right? So what I'm saying is, you have one length element on right hand side. You can take another length element having same length on the left hand side of the ring at same angle. So it will also produce same amount of electric field at this point. So the electric field due to this one is suppose d bar dash. But the magnitude of d bar and d bar dash is equal. Now, if we resolve them along two components, so what do we get? So if we resolve these two, d and d dash along two components, so to resolve we need some angle, right? So this is an angle theta because this is vertically opposite of this angle. So this angle is theta and this angle is also theta because it is vertically opposite of this angle. So now, because this angle is theta, component here, component along y-axis we can say would be d cos theta, and component of this electric field along y-axis would be d cos theta. So these components are in same direction, right? These components are in same direction. So we have d cos theta due to this one and d cos theta due to this electric field. They get added. And if we look at the components along x-axis, so what happens to the components along x-axis? They are directed in opposite direction. Okay, so this was d dash cos theta. So you have d dash sine theta and d dash, sorry, not d dash, d sine theta. So they are acting along x-axis, but they are acting opposite to each other. So this component and this component, this component and this component, they get cancelled out. So what does this mean? If we consider n number of such small elements on one side, for each element, for each length element, we'll have another length element on left hand side which has same length, which is at same angle. So the sine component of the electric field due to one length element would be cancelled by the sine component of the electric field due to another length element, and their cos components get added up, and that's why the net electric field will be just sum of cos components of all such length elements taken from here till here. Got this? Yes, no? Okay, so I can say horizontal components of the electric field get cancelled out. Electric field due to all length elements get cancelled out, and the vertical component or the components of electric field, sorry, don't know why do I make this mistake. Okay, so I always eat up that L while writing the field. Anyways, components of electric field along vertical axis get added. Okay, so therefore what we can say is the net electric field is along y-axis. Okay, so net electric field is along y-axis and it is E equals to, now if we take summation of the electric field due to all such length elements, and we take continuous summation, okay, continuous addition. That means actually we take an integral. Okay, so we take an integral. So integral of what? Integral of the electric field due to vertical components of electric field due to all small length elements. So it is dE multiplied by what was the vertical component? Cos of theta, right? Then what is dE? So dE is electric field due to one such small length element. So how much is dE? It is 1 upon 4 pi epsilon naught multiplied by dq upon r square, because charge on one such small length element is dq, right? So electric field due to that would be 1 upon 4 pi epsilon naught multiplied by dq over this distance square, r square. Okay, so we can put that here. So we get 1 upon 4 pi epsilon naught multiplied by dq divided by r square cos of theta. Now here you can see there are two variables. One is theta and one is this charge. And charge will depend on what? Length of the element, right? Charge dq is lambda times dl. So we can put that, and this was capital R. Okay, so it is 1 upon 4 pi epsilon naught multiplied by dq is lambda times dl divided by r square cos of theta. So here we see that there are two variables. One is the length of the element, another one is theta. So either we have to convert this length to theta, or we have to convert theta to length, right? So converting dl to theta is easier. Okay, changing this variable from length to theta is easier, right? So see how. If you take small length element here, if you take small length element here, it subtends an angle d theta. Let's call the angle d theta because this is small length element dl. It subtends an angle d theta at the center. Okay, so this angle, this much angle is d theta. And how can you write this angle? So we know angle is equal to r divided by radius. So how much is length of r? Length of r is length of that small length element or charge element, we can say. So it is equal to dl. So d theta is arc upon radius, that is dl divided by r, and therefore we can write dl is equal to r multiplied by d theta, right? So we have converted dl to, okay, we have changed this dl to theta in terms of theta. We have written it. So now we have only one variable, and these things, okay, we'll take them outside afterwards. So it is 1 upon 4 pi epsilon naught multiplied by, you have lambda multiplied by dl. dl is r d theta, and in denominator you have r square cos of theta, right? So this r square, if you divide by r, one r would be left, and lambda divided by 4 pi epsilon naught r, you can take it outside, right? So let's do that. So I will take lambda divided by 4 pi epsilon naught r outside, and now we just have integral of cos theta d theta. Okay, now question is, what are the limits of this integral? What are the limits of this integral? Okay, so see, the theta will change from here to here. Theta will change from here to here. So if you measure theta towards left hand side, it is positive angle. If you measure it towards right hand side, I mean, what do I mean by left hand and right hand? If you measure it anti-clockwise, it is positive angle. If you measure it clockwise, it is negative angle. So this is minus pi by 2, minus 90 degrees, or minus pi by 2. This is pi by 2, right? Okay. So the limits of integral are minus pi by 2 and pi by 2. So now integral of cos theta d theta is very simple. What is the integral? Sine theta, right? Because derivative of sine theta is cos theta. So we have E equals to lambda divided by 4 pi epsilon naught r multiplied by sine theta. And what are the limits? So limits are minus pi by 2 and pi by 2. So it is lambda divided by 4 pi epsilon naught r. What is sine of pi by 2? Okay, so let's put limits. Sine of upper limit, sine of lower limit. So sine of pi by 2 minus sine of minus pi by 2. So what is sine of 90 degrees or pi by 2? It's 1. And we know sine of minus of theta is equal to minus sine theta, right? So sine of minus pi by 2 is minus sine of pi by 2. That means it is minus 1. Okay. So this is lambda divided by 4 pi epsilon naught r, 1 minus minus 1. That is, can substitute that. Sorry. Okay. 1 minus minus 1 is 2. Right? This minus minus is plus. So 1 plus 1 is 2. And then you can divide this 4 by 2. So you get lambda divided by 2 pi epsilon naught r. So this is the electric field. Lambda divided by 2 pi epsilon naught r. This is the electric field due to a semicircular ring. Is it clear? Yes, no? Okay, good. And then if we want, we can substitute lambda. What is lambda? Let's check. So it is q divided by pi r. So if you substitute that, q divided by pi r here, so lambda will replace by q divided by pi r. So in denominator we have 1 pi and r already there. So it will be pi square r square in denominator. So we get electric field due to a semicircular ring is q divided by 2 pi square epsilon naught r square. Okay, so this is the formula. So if lambda is given in the problem, we'll use this formula. If charge is given, we can use this formula. So this was electric field due to a semicircular ring. Next, we will find out the electric field due to a ring. So let's find out the electric field. Electric field due to a charged ring, uniformly charged ring. Yes, let's find out electric field due to a uniformly charged ring at a point on the axis of the ring. So we have, I'm sorry, let me draw it. Can I draw ellipse using this? Yeah. Oh, it's good. Oh, very good. So we have this charged ring, and charge on the ring is suppose plus q. So there is a positive charge uniformly distributed all over the length of this ring, and we want to find out its electric field at this point. So this is an axial point. So what is an axial point for a ring? So if you take a ring, this is suppose center of the ring. If you draw a perpendicular on the center or passing through that center, okay, perpendicular meaning a line which is perpendicular to plane of the ring. Okay, so if you draw a perpendicular to the plane of ring passing through the center, it is known as axis of the ring. Okay, so we want to find out electric field due to this ring at this point, an axial point. This is point P. Let's call it P or anything. So what will we do? We'll do the same thing that we have done in the last case in case of semicircular ring. First of all, we'll define the linear charge density. Okay, so linear charge density for a ring, lambda equals to charge upon length, and that is q divided by 2 pi r. Now we have full ring, so it is q divided by 2 pi r. 2 pi r is the length. Then we'll take a small length element. So let's take a small length element. Let's consider it here. This is our small length element having length dl, and charge on that length element would be what? Lambda times dl. Okay, so now suppose capital R is the radius of this ring, x is the x is the distance of point P from the center of the ring. Okay, therefore this distance we can find out using Pythagoras theorem, right? So distance of this small length element from point P can be found out using Pythagoras theorem. So suppose it is equal to r. Suppose this distance is small r. So using Pythagoras theorem we can write r square is equal to capital R square plus x square. Okay, I'm sorry. All right. So the electric field due to small length element is suppose dE. First of all, the dq is suppose charge on dl. So dq is equal to lambda times dl, the linear charge density multiplied by its length. So electric field due to this length element dl would be directed like this along this direction. Okay, radially outwards you can say towards the point P. So the electric field is suppose so let's call that electric field D. So D is the electric field due to dl. Now what we can do is we can consider another length element having same length. Now at diametrically opposite point. So this is another length element dl, or you can call it dl prime, dl dash. So it is diametrically opposite to dl. Now it will also produce some electric field because it will also have same charge as that of this length element because their lengths are same, and distance of this length element from this point P is also same as that of distance of this length element from point P. So it will also produce same amount of electric field, but its direction would be different. So that electric field would be directed along this line. Okay, and how much would be its magnitude? Its magnitude would be this much, same as that of magnitude of the electric field produced by this length element. Okay, so let's call this one as dE prime. Then now what we can do is we can resolve them along two components, two perpendicular components. So we can see the vertical components will get cancelled out and horizontal components will get added up. Okay, so see, suppose that this angle is theta. So this angle would be theta, this angle would be theta, right? So what are horizontal components of d dash and d? They are d dash cos theta, d cos theta. This is horizontal component of electric field due to d dash. This is horizontal component due to d. They are in same direction, so they get added up. And what about components perpendicular to the axis? Instead of saying horizontal and vertical, I will say component, sorry. So instead of saying horizontal and vertical, I would say components along axis and perpendicular to the axis. Okay. So components perpendicular to the axis, they get cancelled out. Okay. So this is, you can say, this is d dash sine theta, and this one, it's not this much. This is d sine theta. Now d dash and d have same magnitude. So this d dash sine theta and d sine theta, they get cancelled out, right? So the electric field due to these two length elements, it is along the axis. It is directed along the axis, outwards along the axis, we can say. Okay, but this is about these two elements only. Now if you have a length element here, if you consider small length element here, and exactly diametrically opposite length element, a length element which is diametrically opposite, so they will produce their electric fields at this point. Now in what direction would their um, components would be directed? In what direction their components would be directed? So there would be a component along the axis, there would be a component perpendicular to axis, but those components will not be vertical, they will be horizontal, right? They will be horizontal, but they will be opposite to each other. This is the point, they will be opposite to each other. Okay, so if you want to imagine why those components would be horizontal, so if you consider length element here and here, it's the same as that of rotating this ring by 90 degrees. So this component and this component, they will come here and here. Okay, sorry, not component, this. Okay, so if you consider a length element here and here, it's same as that of considering the ring to be rotated by 90 degrees. So what will happen? This length element and this length element, they themselves will come at this point and at this point. Okay, here and here. Now what will happen to their components of electric fields produced by them? So those components will also rotate by 90 degrees, right? They will rotate by 90 degrees. Okay, so if you rotate them by 90 degrees, then these components which are perpendicular to axis, they will be directed like this. Okay, they will be directed like this. They will be in horizontal direction. Okay, they were vertical, now they are horizontal. But still, the point is they will get cancelled out, and the components along the axis will get added up. Got it? So this you can do for any two length elements. So if you consider a length element here, you will have a length element like this. So their electric fields, they will produce their electric fields, and the horizontal component, or you can say component along the axis, they will get added up. Components perpendicular to axis, they will get cancelled out. So the net electric field due to this ring is along the axis. Now, what would be net electric field? So we can say E is the net electric field. It is summation of the axial components of the electric fields produced by all such kind of length elements. So it is integral of d cos of theta, we can say. And what is d? So let's write d. So d is equal to 1 upon 4 pi epsilon naught multiplied by this charge dq divided by this r square. Okay, so it's 1 upon 4 pi epsilon naught multiplied by dq divided by r square multiplied by cos theta we have. So this is equal to integral of 1 upon 4 pi epsilon naught multiplied by dq. So dq is lambda times dl, this lambda times dl divided by we have r square and cos theta. So is this theta a constant or a variable? The question is this theta a constant or is it a variable? Constant, right? It's a constant. Okay, you consider any length element anywhere on this ring, the length element will be on the ring only. So this is the angle theta. So if you join that length element to this point, any length element, its distance from this point is equal to the small r, which is what you can say the small r square is equal to x square plus r square, right? So this r and x, they make some angle which will be constant, right? So theta is constant. Okay, and let's write this, that r square is equal to x square plus capital R square. Now, what is cos of theta? We want cos of theta, right? So what is cos theta in this triangle? It is adjacent side divided by hypotenuse, x divided by r. Okay, so it is x divided by r. We can take now lambda 4 pi epsilon naught r square, this r which will become r cube, and x all outside of the integral, right? Because x is also a constant. Distance of this point P from the center, it is fixed. So x is also constant. So you take it outside of the integral, 1 upon 4 pi epsilon naught multiplied by lambda times x divided by r cube. This is all we have. And then we are just left with the integral of dl. So what will be limits for this integration? Limits of this integration would be 0 to 2 pi, 2 pi r, right? The minimum length is 0, and what is the maximum length then you can consider on this circle? So the maximum length is the length of circle itself, the circumference. So minimum length is 0, maximum length is 2 pi r, and this is very simple integral. The integral of dl is just l, the length, and if you substitute the upper and lower limits, because lower limit is 0, it is just upper limit, so it is 2 pi r, right? So if you substitute that, you will get 1 upon 4 pi epsilon naught lambda upon r cube multiplied by 2 pi r. So A is equal to 1 upon 4 pi epsilon naught multiplied by lambda x divided by, not this r, small r cube multiplied by 2 pi r. This is the electric field. Now some cancellations will happen, but before that we can substitute lambda, right? We can substitute lambda. So let's do this. Let's keep one formula in terms of lambda and one formula without lambda. Okay. So if uh, you have pi and pi which gets cancelled out, then 4 divided by 2 will give us 2. So it is 1 upon 2 epsilon naught r cube and in numerator you have lambda rx, lambda times rx. Okay, r lambda x divided by 2 epsilon naught r cube. And what is r? So small r is, we have r square equals to capital R square plus x square raised to, okay, r square is equal to capital R square plus x square, right? We have small r square equals to capital R square plus x square, and therefore if I want r, it is r square plus x square raised to half, square root of that, and we have cube of that small r here, so it is equal to what? Lambda times rx divided by 2 epsilon naught r square plus x square raised to 3 by 2. This is one formula that you get. Okay, then we'll substitute lambda. So if you substitute lambda, what is lambda? It's q divided by 2 pi r. Okay, it is q divided by 2 pi r. So you get quite a simple formula, 1 upon 4 pi epsilon naught multiplied by lambda, which is q divided by 2 pi r multiplied by small r cube multiplied by this x into 2 pi r. This is not x, okay? X multiplied by 2 pi r. This 2 pi r and 2 pi r gets cancelled out. So we get a formula which is simple to memorize. So E is equal to what? 1 upon 4 pi epsilon naught multiplied by qx divided by small r cube. But what is small r? Small r is r square plus x square raised to half. So we'll substitute that. It will be 3 by 2 because we have cube of it. 3 by. So we get this another formula which is actually quite simple to memorize compared to this one. So we'll memorize this. Okay. And if lambda is given in the problem, what we can do is we can substitute q equals to lambda multiplied by 2 pi r. That's it. Now we have solved electric field due to a semicircular ring. We have solved electric field due to a ring on an axial point, and we can see that these problems are a little bit complicated, right? Little bit involved, we can say, because they we need to evaluate some integral while solving these problems. So these are somewhat easier problems. These are easiest of all. Now if we take a line charge, what I mean by line charge, straight wire. Okay, if you take straight wire, then if you want to find out electric field due to a charged straight wire, then the integral that will come, it is quite difficult. Okay, it's quite difficult to solve. So this is for a linear charge only. Then we have surface charge distribution. So suppose you have a rectangular sheet the charge is uniformly distributed all over the surface area of the sheet, right? Then now how will you find out the electric field due to this charge sheet at any point? How will you find out electric field due to this charge sheet at, let's suppose, this point P? So what you do is you take small section of this area. You will take small section of this area like this. Let's suppose this much section, which has area dA, and then it will have some charge which we know that will define the surface charge density. Okay, will define the surface charge density given by what? Sigma equals to charge upon surface area. Then charge on this small section dq is equal to what? dq is equal to sigma multiplied by dA. And then we can find out electric field due to this small section, which will be equal to 1 upon 4 pi epsilon naught dq divided by this r square that we'll have to find out. Okay, that r square would be this distance square plus this distance square, right? So then what we'll have to do is we'll have to integrate all that. So we'll have to integrate this electric field dE. That means you will have to integrate 1 upon 4 pi epsilon naught dq, which is sigma into dA, divided by r square, right? And that r square would be this distance square. You can call it x, or let's call it r. Okay, this distance square plus this distance square. This distance is suppose x. Now here, what are the variables? X is a variable because you can take a small section, small portion of this area here. You can take it here. Okay, you can take it here. So x is a variable. Then this dA itself is a variable. Okay, so you can take small surface area. You can take slightly bigger surface area. So this is a variable. Okay, dA is a variable. R square is also a variable. So what you will have to do is the net electric field is sigma you can take out, 4 pi epsilon naught you can take out. So it will be integral of dA divided by r square. Okay, and what is dA? What is dA? It's small surface area. If you want to integrate it, now dA you can write, let's suppose this is xy plane. So dA can be written as what? This is suppose your dA. It can be written as dx multiplied by dy, right? It can be written as dx multiplied by dy. So you can write this as sigma upon 4 pi epsilon naught multiplied by integral of dx dy upon r square. Okay, so this r square can be written as this r square plus, now since I have written I have considered two coordinates. Okay, so in place of this x you can take small r. Okay, let's suppose you take small r, which can be written as what? Or let's suppose you take some variable. Okay, this is not x, this is suppose rho or something. So here, see, if you talk about this plane only, so rho bar will be equal to what? You can say it is x bar plus y bar. Okay, so rho square will be equal to what? X square plus y square, and this is small r. Okay, so small r square is rho square plus r square. That means small r square will be x square plus y square plus this r square, right? So think about this integral now. So you will have x square plus y square plus r square. Okay, so this is an integral in x and y. So this is not a single integral, this is double integral. Okay, this is a double integral. This is for surface charge density. So this will come when you have a sheet, rectangular sheet, circular sheet, or let's suppose any kind of charge sheet, or if you have a shell, in that case also this kind of integral will come. Then if you have volume charge distribution, what will happen? You will get triple integral, right? You will have dx, dy, dz. Okay, because the charge is distributed in the volume of that material. Okay, so you will have to find out electric field, you will find out dq. Dq will be equal to what? It will be volume charge density multiplied by dv, as we learned yesterday. Okay, and what is dv? Dv is the volume, small volume. Okay, dv is small volume. So it is dx multiplied by dy multiplied by this dz. Dx, dy, dz. Okay, so it will involve triple integral. Finding out electric field due to that kind of a body will involve a triple integral. So it gets more and more complicated, right? So now we don't want to solve integrals. We don't want to solve integrals. We want to solve problems easily. So that's why, I mean, not we, Gauss was a physicist who found a theorem called Gauss's theorem. Okay, he found a theorem called Gauss's theorem. If we use that theorem and find out the electric fields due to these kind of surfaces, which we call symmetric surfaces, okay, so Gauss's theorem allows us to find out electric fields due to symmetric surfaces without solving these kind of integrals. Okay, and that's what we'll see now, if time permits. Yeah, so is this clear? So now we cannot keep on doing this thing, we cannot keep on solving integrals. I mean, if we can, if we have enormous amount of time, we can do this. Okay, but we don't want to complicate our lives, we want to simplify it. Okay, so that's why we make use of Gauss's theorem. So to understand Gauss's theorem, we need to understand the electric flux. Okay, so all right, is this thing clear? The whatever arguments I passed now, even if it is not clear, it's not relevant. I mean, it is relevant, but it's not so important. Okay, but the main thing is, in order to avoid integrals, we make use of Gauss's theorem. That's it, to simplify the problems. Okay, so to understand Gauss's theorem, we need to understand the electric flux. All right. So now let's talk about the electric flux. What is electric flux? So let's suppose there is some electric field in some region. For simplicity, let's consider uniform electric field only. So this is uniform electric field in this region, right? We know that uniform electric field can be shown by equidistant parallel lines. So this is uniform electric field. And now these electric field lines, suppose they pass through some surface. So let's consider surface like this, a rectangular surface which is kept like this. So imagine this. This is kind of 3D diagram. Okay. So the surface has some area. Let's call it A. A is the area of the surface. A is the area of the surface. So number of electric field lines that pass through this surface is known as the electric flux. So what is electric flux? Electric flux means number of electric field lines. This is a symbol for writing number. Okay, high. So number of electric field lines passing normally through a surface. Okay. So now we will consider that the electric field, the magnitude of electric field is directly proportional to the electric field lines. E is directly proportional to the number of electric field lines. Okay. So the field lines that are passing through this area can be written as E multiplied by the area. We can write it as E multiplied by area. So electric flux will denote by letter phi. Phi is equal to E multiplied by area. Now see, electric field is a vector quantity. Electric field is a vector quantity. So if you keep this area like this, maximum number of electric field lines will pass through it. Now, what if you keep area like this? Okay, so these are electric field lines, suppose. Okay, these are electric field lines. If you keep an area like this, okay, so electric field lines are coming like this. Area is perpendicular to electric field lines. Then maximum number of electric field lines will pass through that area. But what will happen if you rotate the area? Less and less number of electric field lines will pass through it. If you keep area like this, then let's suppose your area is like this and the electric field lines are passing like this. Are any electric field lines passing through the area? They are not. Okay. So the orientation of area matters. The orientation of area matters, right? So that's why electric flux is the number of electric field lines passing normally. Normally means perpendicular to an area. So for this area, the area and electric field lines are perpendicular to each other. Now let's imagine this kind of an area. Let's imagine this kind of an area. All right. So see, this is much bigger area compared to this area, right? This area is much bigger. So these electric field lines are passing through this area. After passing through this area, they will pass through this area also. But what about the number of electric field lines passing through this area? If you compare the number of electric field lines passing through this area and this area, they are equal, right? The electric field lines passing through this area and through this area, they are equal. So if we just take the product of E and A, electric field, and A, area, okay, if we just take the magnitude of area, then it makes no sense, because we can very easily see that the electric field lines passing through this area A, and the other one, let's call it A dash. So we can easily see, we can easily imagine that electric field lines passing through this area and this area, they are equal, number is equal, but this area is much bigger. So if you just take the product of E and A dash, what will you get? You will get much more number, much more bigger number, right? So this is not how we can define the flux. This is not how we can define the flux. So see what we can do. So suppose this is X and this is L. Okay. So this side is common between this area A and A dash. this side is common, and this side and this side is different. This side and this side is different. So let's suppose this length, okay, this length is L dash. So now this angle is suppose theta. What would be theta in terms of this length and this length? We can say cos of theta. Cos of theta is equal to L divided by L dash. Okay, cos of theta is L upon L dash. So now if I multiply cos of theta is L divided by L dash. I'll multiply the right hand side by x. Numerator will multiply by x. Denominator I will multiply by x. So what do I get? I get, see, in numerator I get a, in denominator I get a dash. Okay, and that means a is equal to a dash cos of theta. Okay, so see now what we can do. So flux through A is electric field multiplied by A. Flux through A is electric field multiplied by A. What is flux through A dash? It is also same number of field lines are passing through A dash also. So I can say flux through A dash it is also same. It is also E multiplied by A. Same number of electric field lines are passing through A dash also. Now I want to write this in terms of A dash. So how can I write this? So I can write this is equal to E multiplied by A dash multiplied by cos of theta. Okay, E multiplied by A dash multiplied by cos of theta, right? And now what is the significance of this angle theta? So see, area in general, in our day-to-day language, area is a scalar quantity. In our day-to-day language, area is a scalar quantity. But in physics or in, okay, when we see applications of electric field or some similar examples, we have to consider area as a vector quantity. Okay, and what is direction of that vector? So direction of the vector is perpendicular to the plane of area. So what will be direction of a bar? So this a is a vector quantity. What is its direction? This is the direction perpendicular to plane of area. What is direction of a dash? Direction of a dash is perpendicular to plane of a dash. So this is the direction of a dash. Okay, this is a dash cap, you can say unit vector in that direction. Okay, or you can say, okay, if you suppose this much is the magnitude of this area, so you can say this is a dash bar. Okay, and now see, it makes sense. So now I can write flux as flux through area A as the dot product of E bar dot A bar. How? See, area is directed along this direction. The electric field is also directed in same direction. So what will be the dot product? It is E multiplied by A multiplied by cos of the angle between two, and angle is 0, cos 0 is 1. So E bar dot A bar will give us what? It will give us phi equals to E into A, E multiplied by A for this area. But what about this area? For this area, if you take E bar dot A bar, it will give you flux. Okay. So what is direction of electric field? It is this direction. What is the direction of area? It is this direction, which is perpendicular to plane of the area. This is the direction. It's perpendicular to plane of area. What is the angle between the electric field lines and this area? So if you think about the angle between electric field lines and this area, so electric field lines are directed like this. This area is directed like this. So this angle is equal to theta. This angle is equal to theta. So this angle is theta. It's the angle between these two areas, right? It's the angle between these two areas. This angle is theta. So cos theta you can write like this. Okay, cos theta you can write like this. So, okay, then this angle and this angle would be equal. Okay, if you rotate those two areas, if you just rotate the two areas, so angle between areas is equal to angle between the perpendiculars to areas. So this, okay, this direction and this direction, it's same. Okay, this is the perpendicular to this area, right? This is the direction of area, perpendicular to plane of area. Okay, so now that way, if we define it, the electric field, the electric flux, then it comes out to be like this. So phi can be written as what? It is dot product of E bar and A bar. Got this? Yes, no?